seen about the graph theory, in which we are seeing about the depth first search, right? And a basic concept of graph theory, in which we have recalled that a graph is a tree if and only if graph is fully connected and graph has no cycle, then can only be a graph will be a tree. In which what we have did, we have find out the adjacency list and we have initialized the adjacency list from the given edges. And let's connect with another approach of this program, right? So another approach is what? So before going to the another approach, right, let's understand first the complexity, okay, of the graph valid tree. And we have gone through the DFS, right? So let's understand the concept, right? So total of what we have given, we have given, let's understand, E is the number of edges, right? Number of edges given, right? And N is given what? N is given number of nodes, right? This is given, see, in the example here and here it is given, right? So creating the adjacency list, it requires initializing a list of length n with a cost of on, right? So what we can say, the cost, if we'll talk about the cost, it is what? O of n, correct? Now then we have to do what? We have to iterate over the nodes and then we have to insert the e edges, right? The given edges we have to get iterate over the edges and then we have to add on to there, right? For a cost of what? We will add O of e, right? So these two will become what? O of n plus e, correct? So this is our time complexity. This is the actual cost, okay? Similarly, if we'll talk about the space complexity, okay, so the space complexity we will find with the help of these two given, okay? First, the adjacency list is a list of n, right? So we have to understand with its inner list with the length that add total of e, right? So total length is what? E he has, and how many length we have to take? We have to take n length. Length should be adjacency list length should be n, and it will add its total. How many edges? This edges, right? So similarly, we can say total it will take O of n plus e spaces, right, for the adjacency list. And the worst case, if we'll use a stack, we will use a stack or queue, yeah, queue, right? In that case, what will happen? N nodes on it, we have to add on that, right? And that will take what? O of n time, right? But if you really talk about everything that we have seen till now, right, that will our O n plus e as a space and time complexity both. But when we are using stack and queue, that will take O of n, okay? Okay, so this is time space complexity, this is time complexity. So let's understand how about the advanced graph theory, in which we will see the iterative depth first search, DFS, and the some iterative way to how we will develop, okay? So first, what is our intuition is, depending on how much graph theory you know, there is a better definition for determining whether or not a graph is a tree, okay? So it depends on you how much you know about the tree, right? For the graph to be a valid tree, it must have exactly how many edges? If n is given the number of node, right? So n minus 1, right? For a valid graph to be a valid tree, for the graph to be a valid tree, what should happen? It must have exactly n minus 1 edges. Okay, n minus 1 edges. Any less, it can't be possible to be fully connected, right? It can't be fully connected. Okay, if you can say fully connected, if it is fully connected, so it should have, it must, you can say, oh sorry, it must n minus 1 edges, should have. Okay, now think about for any more, it has contain a cycle, right? It has contain a cycle. Or let's understand, additionally we can say that if the graph is fully connected, right, if the graph is fully connected and contains exactly what, n minus 1 edges, we can say if the graph is fully connected and it contains n minus 1 edges, then what, it can't possible contain a cycle, right? It can't possible contain a cycle, must be a tree, right? Because if you talk about here, that we are talking about how many nodes is given, total 5 node is given, right? So how many is it should be, right? So let's count, 1 2 3 4. It's n minus 1 is 4 edges we have here. See, 1 2 3 and 4, right? So that's why it can't be possible contain a cycle and therefore must be a tree. These facts are fairly straightforward to prove. We want to go into why they are true here. But if you are not familiar with these facts, then we recommend reading up on graph theory. Okay, so it is very important to be confident with the graph theory in order to pass the interview at a top tech companies, right? So going by the definition, our algorithm needs to do what? First we will check what? Whether or not there are n minus 1 edges. First. Second, and if not, you can say if not, then we have to return what? False. We will return false. So in the second condition, we will check in the algorithm, check whether or not graph is fully connected. Okay, check whether or not graph is fully connected. Then if graph is fully connected, we will return what? Graph is fully connected. Whether or not graph is fully connected, what we will do? If it is false, right, we will return true. That time we will return what? True. But if not, then we will return, if not, then we will return what? False. Okay, now we have to recall the most complicated part of the approach one, that was we are checking whether or not the graph contains cycle, right? So this is because this was because in an undirected graph, right, we needed to be careful of trivial cycle, right? Remember, I was talking about A, B and A, that is our trivial cycle, right? So we have to whether checking whether or not graph is fully connected, which is straightforward, right? We simply check if all nodes were reached from search starting at a starting node, right? Single node from parent to all its kids, child node. Like before we can check for the connectivity using what? Either recursive DFS that we have seen already, or iterative DFS, either recursive or iterative. So, or iterative, we can also use what? Iterative BFS, breadth first search, that we have already seen these things, right? We still need to use a scene set to prevent the algorithm, correct? We were doing that using the iterative DFS recursive, right? BFS. So we still need to use a scene to set to prevent the algorithm getting caught in an infinite loop. And if there are indeed cycles, right, what we have to do? We have to prevent looping on the trivial cycle. So what we can do, we'll go in the code section. Let me give me 1 minute. What we can do here, I'll teach you here. I'll say that we have iterative DFS. Okay, this is our iterative DFS. Okay, and again we will provide code for all these variant. Let's understand a little bit. So if I'll talk about here, what we have public, it was public boolean, right? And then we were using what? Valid tree, remember? Then we were passing int number of node, then we are passing what? All its edges, right? That is our 2D array, and that is called our edges, right? This is done. Now first we should always check if edges dot length not equal to n minus 1, correct? Then we will return what? We will return false. Okay, first condition. Then we will make what? Adjacency list. Then we have to make adjacency list, right? How will make that? Let's understand. This is we will take list of list, and that will take our integer that we have already did, right? And this is called adjacency list, and equal to new, we will take array list, right? Array list we will do. Now we have to initialize the, right? So what we will do, we will start with int I equal to 0, and then we will go to I less than n and I plus plus. Now what we will do, we have adjacency list dot, we will do add, and we will put what? New array list, new array list we will do. Okay, do like this. Okay, these two things is done. Now after initializing, we have to put the value, right? How we will do that? We'll make a for, then we will say int at one time we will take one by one is one is, and it will come from what? Edges, correct? And here on the edge we will add on to the adjacent list, right? So we have adjacency list, and then we will do add, right? Add at what? At the given edge, right? Edge 0, and then we will add here edge 0 at 1, 0 at 1 we will do. That is also done. Similarly, the adjacency list will remain similar. We will do add here also, and we will pass what here? We will pass here edge, and it will 1, and here we will add edge at what? 0. means all the nodes are added onto the adjacent list. Now your value we have on the adjacent list, right? Now B used to do what? We have stack. What we have? We have stack. We'll put here. We'll take stack, right? And this stack will our integer stack and equal to new stack. Correct? Yeah. Okay. Done. Now what we will do? We will make. We will take a scene, right? We have set. Then we have integer, and this is our scene equal to new asset. This is also done. Now what we will do? We will push onto a stack dot push will pass the 0 node, first node. Then we will do on the set we will add scene dot add 0, right? This two is done. After that what we are doing, we have the while loop, right? In the while loop we will taking if set stack, right? Stack is empty. If this is not empty, then we will go to what? Stack dot will do pop, and we will get onto our node, and we will make a for loop. Now we'll get its neighbor nei. It will come from what? Adjacency list dot get node, and we will get all its neighbor. Now we will check what? If we will make condition if nei or scene contain scene dot contains what? Nei, right? Neighbor. Then what we will do? We will continue, right? If not, right? If not, then we will go to next part and we'll say update the record. Scene dot add will add the neighbor onto the scene, and then we will add on the stack dot push, right? It was nei. So this part is done. For while, and after the while we will take return what? We will return here scene dot size equal to n. Remember? So this is done. So if the size is equal to n, means it's true. Correct? Now you can think about, this was our iterative depth first search. Now we'll talk about recursive depth first search, and then we'll do coding. Okay, so this is our recursive DFS. Okay, in the recursive DFS, what we have to do? We have a class, and class will take what? Solution. Class name is solution, and we'll take two things. We'll take private. We have to take list, private list, and we'll say this a list of integer. It will contain list of integer, and that is what? That is, we can say adjacency list, right? Adjacency list, and this is new array list. This is done. Okay, now we'll take a private, this we can set of integer, and this is our we'll say scene equal to new has set done. We have taken two adjacency list and this. Now we'll go to the boolean, right? Boolean method. We have public boolean valid tree, right? Valid tree in which we will pass int node and int ages. Correct? So two things we have sent. Now we'll check if ages not equal to ages length not equal to what? N minus 1, right? Means we have to return false. Correct? Means n minus 1 ages we don't have, so it is not connected, right? Now we will make the adjacency list. How? We will initialize our adjacency list. How we will do that? We'll take for loop. Int will start from I equal to 0, then I is less than n and I plus plus. All the nodes at the order, all the nodes we will do adjacency list dot add. What we will pass? We'll pass new array list and then we will pass this one. Correct? Here this is also done. What we are doing there? We will after initializing we will put the data, and for that all the edges we have to traverse. We have age 1. This is our single array, we can say. It will come from where? All the ages is already given in the method declaration. Then what we will have to do? We have to take adjacency list dot add. We have already did this. Add what? At age 0. At age 0 we will add what? Age at 1. We will do here. That's all done. Now we will take here 1 and here we will take 0, right? Here that's done. Okay, now our adjacency list has been initialized and it's been you can say have the data now, right? Now we will call what? A DFS utility method, DFS, and you can say utility. This will work for DFS, right? We'll pass what? Our starting node from where the DFS will start, and then we will return what? We'll say scene dot size, right? If size equal to n, if it is true it will return true that graph is valid or not, right? So this is all about we have. Means we have to create what? DFS utility, right? So let's go and we'll create the DFS utility method, right? So in the DFS utility method it will take what? It should be first it should be public, second void, we are not returning anything, only give it's working utility, right? And the DFS utility what we pass? The node. I will pass the node 0 we have passed in starting. So this is our first node, root node. Then we will check if scene dot, this is reference variable, so we can call here scene dot contains what? Our node, this given node 0 yeah, root node you can say. We will pass, then we will be returned here. We will not do anything if it already seen. If not, then first we will add on the scene, then add on where scene, and what we will add, this node. Now we will move to all the neighbors. For we will go to int, and that is our what, neighbor. This time we will write full this neighbor, and we'll say this will come from what, adjacency list dot we'll say get method, right, and we'll get this node. At this node we have its all neighbor, right, so here we are, one neighbor will got, will pass in dfs utility method, and it will pass what, its neighbor node. Now neighbor node will pass, and all the neighbor it will traverse, and that's all we are doing for here. Okay, and this will, we will close the class. Okay, so as you can see that it's very easy, right, to do recursive. Now one more thing we have talked, that is what, uh, iterative BFS, right? So let's understand here, then we will recap again. iterative BFS. Okay, iterative BFS. So let's talk about the function. We have public boolean valid tree, right, in which we are passing what, one we are passing node, and then we were passing int all the ages of this. Okay, now first we will check if ages dot size, not size, its length, right, ages dot length not equal to its n, right, n minus 1 means it is connected, it is not connected, sorry, and then we will return here false, will not do anything. If not, then we will make the adjacency list, right. How we will do that, we have already seen these things. So we will take integer list of integers, and this is called our adjacency list. I'll give the short name now, and this is our new array list, like this short name. Now we will initialize this adjacency list. How we will do that, we will start with for int I equal to 0, it will go to what, I should be less than n and I plus plus. Then we have adjacency list, then what we will do on this list, that we will to add, will pass is at no, sorry, new, we'll do new array list, like this, that's all. Now we have to add all the value at here. Int we'll take one age at a time from the ages, and this as will add on the adjacency list dot add, will pass at 0 what we have, at what we have at 1, 2 pairs we have for all. Next time if we'll add, will pass what, 1, we will pass at is at 1. Similarly we'll do add is at 0, will pass here, and that's all. Okay, so our adjacency list is done, right. Now what we were using, let's go to here, we were using a queue in the BFS, right. This is our queue, this will take integers, right, and this is our queue equal to new, we'll take linked list, right? Linked list is our queue. Now what we have to do, we have to take a visited, we'll store all the visited in scene, and that is our new has set, correct? Yeah. Now we have queue, so we will add queue dot offer. We will add the root node, that is 0, and then we will update our scene. That what we will do, scene dot will do add that we have already visited the root node. Two things done, three things is done already, right? After this, what we should do always, we will make a while loop, and we should check if queue dot is empty. If queue is not empty, then what we will do, we'll go to queue and we will remove, we'll do queue dot poll. So we will return the value, and that is our what, int node. Now what we have to do, we have to go all to its all neighbor of this node, right? So let's this is our parent node, that is root node. So we have our its all its neighbor, right? It will come from where, the adjacency list. Adjacency list we have, and we are getting using get, and we will pass this node. So all its neighbor will come from there, in which we will see, we will check in the scene if this neighbor, right? If scene dot contains, scene dot contains, what contains, this neighbor, means we have already visited this one, and so that we can say we will not go, if it contains, right, then we will what do, we will not do this anything for this, we will skip this one and we will move to next. If it is not, then we will add on to the scene first, and we'll say let's add neighbor onto the scene that is visited. Now what we will do, we will add onto the queue, we'll do again the offer, we'll pass our neighbor here. Both is done, correct? And finally we will close this for loop, and then while loop will close, and we'll say we'll return what, scene dot, we'll do size, and we'll say equal to what, n, correct? Then we will return here. So let's recap now. I was talking about the graph valid tree, right, in which we have recapped that first we have gone through iterative DFS, in which what we were doing, give me 1 minute, okay, I'll take another cloud frame, yeah. So I was talking about iterative BFS, okay, DFS. So what we have the method valid tree, in which we were passing node n, and then we were passing all its edges, right? Then what we have to do, first we have to check if this is all the edges is connected or not, right? And so that what we have to see, only we have to check if n-1 is there, right? How many node, n-1? So all edges length should not equal to n-1, means it is not connected, right? If it all the nodes are connected, means that is what is equal to n-1. So I'm talking about if not connect, if all the nodes are not connected, means edges dot length not equal to n-1, and that's why what we are doing, we are returning false. Next time what will happen, we will make the adjacency list. How we will making, this is our adjacency list and this is our array list, right? So we are making list of list. Now what we will do, we will initialize here the array list, adjacency list, and then we will put all the value. We will do first adjacency list dot add at is at 0, we will add what, 1, means as node 0 have its children what 1, and similarly we'll saying is 1 have its parent 0. Like that we will maintain all its neighbor onto the adjacency list. The best part is that we will use two things. We will take stack and another is scene. Stack will store its all node and scene will add all its visited node. So initially I am taking 0 the root node, right? This is our root node. Then we will go to 1, then we will go to 2, then we will go to 3, right? These are our nodes, right? And this will go to our 4, right? This node. So in starting I am passing this root node, right, 0, and I am saying that this root node is now seen. Okay, now we will make a condition while loop and we'll check on the stack, right? But we have just added the here on the stack we have added 0 node, right, root node. So this loop will work because we are checking if stack is not empty, means this time stack is not empty. A stack have what? This is our stack. We have pushed one thing here 0, and in the set if we will talk about the set, we have on the set like this 0. Okay, this two thing is done. Now if we'll talk about this while loop, right? So now stack is not empty. This is what? Stack. This is our stack and this is our set scene. This is our scene and this is our stack. Okay, now the while loop will work. Now we have to remove from the what? Stack. So we have to remove from the stack. We are removing, sorry, yeah, we can say we are removing this root node from the stack, and that is what? Our node. Okay, now we'll check here the if the adjacency list dot get node. If adjacency list dot get node means this one, right? It's neighbor. What is the neighbor? Neighbor is this is neighbor, this is neighbor, and this is neighbor. Okay, so we'll get all the neighbors, right, one by one. So 3 first it will come 1 in what? This is the neighbor 1. So we'll check on the scene, right? In the scene, this is our scene, right, and this is remaining. So in the scene we don't have what? 1, right? So it will what happen? It will go to first here. We'll check scene dot contains any I, no. Then we will continue. We'll add onto the stack, right? So now we have already removed what? 0, right? Next time it will what happen? We are adding here 1. Okay, here 1. Now sorry, on the scene we will add 1 here, and then we will add on the stack. That is done. That is we have did here. Next time this for loops is completed. Next another is this is done. Now we will go to 2. Another neighbor is 2. Then we will come to here again, and this scene dot add nei will do. We will add onto the scene first here 2, and then we will add what? We will do add 2 here, not 2. Okay, similarly we'll come to this node 3, and now the 3 node will come on the stack, and we will update our scene also here. Okay, so this is done. Similarly, what happened? This for loop is completed for all these nodes. Now this loop will come again here, right? Now we'll pop the stack dot pop. Then it will start remove from what? We'll remove 3. We'll check 3 children. We don't have 3 children, right? We'll check on the stack. Similarly it will go and will find its neighbor. We don't have any neighbor, right? We don't have any neighbor for 3. Okay, but if we'll see the adjacency list, it will return what? 0 as its what? Neighbor. So one time it will run, and so that if it will check here that, oh, this 0 node 0 that we are passing here as a neighbor, right? This one, this is already in the scene here, right? It is already in the scene. So what we will do? We will continue. So there 3 has only 1, so he will not work for these 2 line of code. So it will continue. It will bypass this line. So next time again it will go for another one, that is for 2, right? Now we will go for the 2. So 2 will come, we will pop the node here, we'll check its neighbor, neighbor is only 0, and it will say that it said scene has already contains the neighbor, like the previous one. So it will go back. Now this part is done, for the 2 is done. Now we will come to what? 1, right? In 1 we will check this one, 1 is done or not. So 1 has 2 nodes, 0 is already visited, and we have the similar way we have on the scene. But now we'll talk about the next neighbor, that is 4, this one. So we'll check for the 4, 4 is not there. Then what we will do, right? We are talking about this one when we are removing from here. So we will add 4. These are not here. Now we have removed already, right? So now we have what? 4, and we have removed this one now. So only one node is at the stack. Stack have only one node, that is 4. Now we have add on to the what? Scene, and there is also we have added on the stack, correct? Finally we'll check the scene size. So if you'll see here how many size we have total 4 size we have, right? And if is equal to n, right, then we'll say, yeah, this is our no sorry, this we have started from 0 to 4, means total size is 5. And how many nodes we have given? N equal to also 5. So it will it will say uh, n equal to 4 now, right? And 4 is the size, correct? It will return true. Similarly, in the recursive way, we have did the same way. Adjacency list we have taken, scene we have taken, right? But we are doing recursive now. Only one thing we will see, that we have taken one DFS utility method, right? And this DFS method will, we have started from what? Root node, right? Then we will go to here, and it will check onto the scene. If it contains the, then it will not do anything, it will not go here, this line, it will return here, okay? But if not the case, then it will go what? It will continue this line. First we will add onto what? On the scene, then we will go for all the neighbors like previously we did, and internally we'll call all its neighbor. Only what we have to maintain this scene. We'll traverse for all the nodes, and we'll all add onto the scene, because we are checking the scene dot size. See here, we are returning scene dot size, the down one, okay? Here we are checking the size, and that's why we have to maintain only the scene, right? So only scene we are doing here. We will add all onto the scene, we do not need to remove from the stack. So we are using only set here, right? We are using only set, and not, we don't have any stack. See, only adjacency list and this one, we don't have stack that we are doing. You see, only what we have, set we have, and adjacency list, okay? We are not using stack. Now there is another approach, that is BFS. That was our recursive DFS. Now this is a iterative BFS, in which what we will take, we'll check by same thing. If the number of edges is not equal to n minus 1, it means all the nodes are not connected, and so we will return false. Again, what we did, we will have our adjacency list. We will initialize all the adjacency list using the new array list, and then we will add all its edges, its all neighbors we will add one by one, okay? Now in recursive BFS we will use queue, right? Queue we will use first, and we will add onto the queue. And to maintain the visited node, we will use what? Scene, right? So first node we will pass, root node we will pass, and then we will update the scene that we have visited root node. Similarly, we will return, we will check the queue is not empty. Then what we will do, we will do queue.poll, we will remove from the queue. Let's assume that this is our queue. This is our queue. Internally, first what we have passed 0 first in, right? So who will go first in first out, right? So queue.poll will do. Now queue is removed, right? Now queue is what? Here. So now queue is removed. Now what will happen?
all its neighbor will come. You know that this is your 0, 1, 2, 3, and this is 4. This is our tree. So we have passed 0 onto the queue, right? And we have removed the from the queue. Now on the node we'll get all its node. Now on the queue, what we have? We have 1, 2, and 3. 3 nodes we have. First one will come here, right? We'll check the first neighbor. Is it containing on the scene? Here it will check. If not, then we will add on to what? Scene and stack. So now scene we have, previously 0 we have, now we have 1. This is our stack, set, and this is our queue. So this queue and this set we have. Now queue dot offer, right? We have added onto the here 1, correct? We have added here. Now we'll go to next time. We'll remove this one first, right? Because we have just queue. We have did queue. Till now we don't have this one here. Next time we'll come here. We have, but one will come first, right? So it will remove first. Then it will remove this. Then it will remove this. And now I will check this one. So when we are at 1, right? Then we will see that we have 4. So we will add a 4 here. So after that we will remove this one. We can do in the recursive way, like we first 1 will come, 2 will come, 3 will come, 4 will come. So we'll remove first this one. So we have added this one. Next time we will remove this one and this one, like that. We will see that also. And finally we will maintain all the similarly we will maintain all its scene, and then we will say that scene dot size equal to n. That's why it is returning its size. So finally, if we'll talk about the complexity, right? So what we have taken the edges, right? So we have taken e is the number of edges if we have, right? And n is the number of what nodes, right? You can say nodes we have and edges we have, right? So when e number of edges, when number of edges not equal to n minus 1, means it is not connected, and we simply returns what? False, because all nodes are not connected. Therefore the worst case is what? E equal to n minus 1. This is the worst case, right? Worst condition you can say, because e is proportional to n, because e is proportional to what? N. And we say that e equal to n to simplify the analysis, right? Because this is our what? E equal to n, correct? These are similar. Now as we said above, right, creating an adjacency list, time complexity is what? When we create adjacency list, time complexity is what? O plus n, right? O, this one, n plus e, sorry, n plus e, n plus e. This was our time complexity, correct? Because e is now bounded by what? N, correct? We can reduce by simply O. We can reduce this what? O n plus n, and that we can say O of n. Got it? I'm saying when we are creating adjacency list, right, it has the time complexity is what? O n plus e, right? O of n plus e. But e is now bounded by what? N, right? This is e equal to n. Got it? So we can say that O of n plus n is O of n. I think you are understanding. Actually we can reduce by slightly O of n, right, to from O of n plus e. So now if we'll talk about the iterative BFA search and depth first search are almost identical. Each node is put onto the stack queue, correct? Each node is put onto the stack or queue, and we ensure that scene set, right? we are using there. Therefore the inner neighbors loops runs once for each node, right? And across all the nodes, the number of cycles this loop looks, let's come here, you see, what we are doing, we are going for all its node, right? All its node one by one, correct? For all its this one. So what we can say, the recursive DFS search, depth first search neighbor loops runs only once for each node. Therefore it is going for, while we are calling for DFS, right, we are going for only one times, right? Let me here, yes, see, it is going for only one time. Only one time we are making this loop, right here. Okay, and that's why we can say that in the total the function is called once for each edge. So it is called what? We can say that E equal to what? N equal to N. And because it's going for what? N times. For all N nodes. N nodes we can say. It is happening for all N nodes. And actually it enters the neighbor loop, right? It moves into the neighbor loops. So if we collectively collect the total number of iteration of the neighbors loop is what? E equal to N. And that's why we can say that complexity is what? O of N, if we'll say. So in both ways, if we'll talk about the DFS, right? Sorry, DFS, or that should be recursive, right? Recursive. So we are going for only one loop for all its neighbors, and so that complexity O of N. So if we'll talk about the space complexity, right? So what we have defined till now, previously we determined that adjacency is what? O of N plus E, or you can write E plus N also. Okay, a space. And we know that simply it is what? O of N, correct? O of N, this is O of N. So in the worst case, the search algorithm will reduce an additional S space O of N. O of N. So this is if all the nodes were on the stack or queue at the same time. So again we can get O of N time, and that's why we can say this is our space complexity. Okay, so this is all I have in this, right? But we will see more depth in this program, and that will come our approach 3, in which we will see the union find, the advanced graph theory. This is our advanced graph theory, and we'll see in the next part of this video. So please like, share and comment. If you have any doubt, please let me know, and if you have come the first time, please subscribe this channel. Thank you so much.